Hello, dear friends. This is Dr. Jaya Joshi from Nagpur, and today I'll be taking lecture on gypsum products. Now, in dentistry, in day-to-day life, we use different types of gypsum products, that is dental plaster, dental stone, dye materials, investment materials, so these materials are very commonly used in dentistry. So basically, what is gypsum? So gypsum is a mineral mined in various parts of the world. Chemically, it is calcium sulfate dihydrate. On heating, it loses water of crystallization and gets converted to calcium sulfate hemihydrate, which is commonly used as a gypsum product in dentistry. Now, we will see the classification of gypsum products. So, according to manufacturing process, the products are classified as by dry calcination, by wet calcination, by boiling with chemicals, and synthetically prepared gypsum products. Another way to classify gypsum products is according to the crystal structure. So, uh, the gypsum products having spongy, irregular, or monoclinic crystals, and gypsum products having prismatic, regular, and monoclinic crystals. Then they're also classified on the basis of its applications or uses, and this is the classification which is given by ADA. So they have classified gypsum products into 5 types. So type 1 is impression plaster. Type 2 is model plaster or simple dental plaster. Type 3 is dental stone or hydrocal. Type 4 is dental stone with high strength, which is also called as dye stone, densite, yeah, improved stone. And type 5 is dental stone with high strength and a high expansion. So these are the 5 types according to ADA. Now coming to the manufacturing process of gypsum products. Now the name of the manufacturing process is calcination. So calcination is nothing but a heating process. So by heating this calcium sulfate dihydrate, which is a gypsum, the water of crystallization is removed and the dihydrate gets converted to hemihydrate. So calcination is nothing but the heating process of gypsum to get the different gypsum products. Now this is the heating cycle, which is given in this diagram. Now initially when you heat calcium sulfate dihydrate from 110 to 130 degrees centigrade, the resulting crystals are of calcium sulfate hemihydrate. That is, we call it as dental plaster or dental stone. If the temperature goes beyond 130 and up to 200 degrees centigrade, we get the crystals of calcium sulfate, that is of hexagonal anhydrite, which is a soluble type of anhydrite. If it is further heated to 1000 degrees centigrade, then the resulting crystals are of orthorhombic anhydrite, which is insoluble type of anhydrite. So this is the heating cycle, and we are interested in the first part, that is heating the calcium sulfate dihydrate at the temperature from 110 to 130 degrees centigrade. Now there are different ways by which we can do this heating, and accordingly we get the crystals. Now, dry calcination. Dry calcination, the name itself is suggesting the gypsum is heated in a pan or a kettle, which is open to atmosphere at the temperature of about 110 to 130 degrees centigrade. As it is heated in an open container, the resulting crystals are irregular, large, and spongy. Coming to wet calcination, again the name itself is suggesting this is carried out under pressure. So gypsum is heated from 110 to 130, that is the same temperature, but in a closed kettle or autoclave under the pressure of 17 pounds per square inch. So the resulting crystals are definitely prismatic, monoclinic, regular, and small. Now we get the gypsum products by dehydration also. So you can boil the gypsum in 30% calcium chloride or 0.5% sodium succinate solution, followed by washing in boiling water, drying, and powdering the particles. Again, here you get fine monoclinic and prismatic crystals. Gypsum product can be synthetically prepared also. Gypsum products is a byproduct. That is, the calcium sulfate hemihydrate is a byproduct in phosphoric acid manufacturing process. So that way also gypsum products are manufactured. But common way to manufacture the gypsum product is by heating calcium sulfate dihydrate, either by dry calcination or by wet calcination. Now coming to the setting reaction. The gypsum or dental plaster or dental stone, we can say now. So they are available in the form of powder. And to use for a particular, for or to get the proper consistency for a particular use, we have to mix dental plaster or dental stone with water. So when calcium sulfate hemihydrate is mixed with water, it regains its water of crystallization, which has been lost during calcination process, and it forms calcium sulfate dihydrate. So this is a very simple setting reaction. It is exactly opposite to that of calcination. In calcination, dihydrate gets converted to hemihydrate by heating. In case of setting reaction, hemihydrate is mixed with water to get a dihydrate. Now there are different theories which has been put forward. So these are colloidal theory, hydration theory, and dissolution precipitation theory, out of which the most accepted theory is dissolution precipitation theory. But the other two theories also we will see in short. Now coming to the colloidal theory. Now colloid is nothing but the fourth state of matter in which you find two phases, that is dispersion medium and dispersed phase. And here the particles are bigger in size. So when you mix hemihydrate with water, it forms a hemihydrate sol. Now, hemihydrate sol is nothing but in which the dispersion medium is water and the dispersed phase is hemihydrate particles. Now, the hemihydrate particle starts dissolving in water and they will form dihydrate. So, next you get a dihydrate sol, in which again the dispersion medium is water and the dispersed phase is dihydrate particles. Later on, more and more dihydrate or the hemihydrate particles will go on dissolving, and one stage will come that you get a dihydrate gel, in which the dispersion medium is dihydrate and the dispersed phase is your water, which is nothing but the excess water. So this is the colloidal theory of setting. The next theory is a hydration theory, that is simple. When you mix hemihydrate and water together, we get the hydration of hemihydrate followed by bonding to the sulfate group, and we get the set dihydrate. So it is simple hydration of hemihydrate, which is converting hemihydrate to dihydrate. Now, the last theory, which is the most accepted one, is a dissolution precipitation theory, which is proposed by a French chemist, Henry Louis Chatelain, and later supported by a German chemist, Van Hoff. Now, this reaction is based on the differences in the solubility of hemihydrate and dihydrate. Hemihydrate being 4 times more soluble than dihydrate. So, this is the basic of the setting reaction. Now, these are the different stages which are found during the setting of hemihydrate. Now, initially, when you mix hemihydrate with powder, the powder particles remain suspended in water and you get a suspension. Later on, the powder particle starts dissolving in water and you get a dissolution phase. Followed by you get a solution, that is hemihydrate is dissolved in water and you get a solution. Now soon this solution becomes saturated. It will become saturated with the addition of hemihydrate. And later on, now here as the hemihydrate is coming in contact with the water, it is forming dihydrate after dissolving in water. So this saturated solution with respect to the formation of dihydrate, it becomes supersaturated. Now, everyone knows that supersaturated solutions are unstable in nature. So whatever dihydrate has been formed, it starts precipitating out of the reaction. Now, once this dihydrate starts precipitating, the remaining solution no longer remains saturated and more hemihydrate starts dissolving in it. So this process continues till all the hemihydrate gets converted to dihydrate. So this is the simple reaction which is explained with the help of diagram. Now here you can see these black particles are nothing but the hemihydrate particles and surrounded by water. They will start dissolving in water and they start grow. Now they grow like a crystal. They grow from the center and they form a star-like appearance, which is called as spherulite, which is nothing but a star-like appearance. So you will find thousands of stars which are growing from the center, which is called as nuclei. Okay. So these are the n number of nuclei of crystallization. So this is, and when these crystals will take up more and more water, they will grow. As they grow more and more, they come closer to each other and they start intermeshing with each other. As all the particles intermesh with each other, the material sets to a hard mass. Initially, this reaction is little slow and the amount of heat which is getting evolved is little less, and this period is called as induction period. So this is a very simple setting reaction. The hemihydrate particles, they are taking up water, they are growing. As they grow more and more, they will come closer to each other. As they come closer to each other, they start intermeshing with each other. When thousands of crystals are intermeshing with each other, the material, the viscosity increases and ultimately it sets to a hard mass. Now coming to the factors affecting setting. Now these are divided into three groups, that is theoretical factors, factors under control of manufacturer, and factors under control of operator. Now we'll see one by one. Now theoretical factors. Now these are mainly based on the theory of dissolution precipitation. So according to these factors, number one is, if you increase the rate of dissolution of hemihydrate, if the rate of dissolution of hemihydrate increases, automatically the rate of reaction will increase and the setting time will decrease. Similarly, if you increase the number of nuclear crystallization, they will come closer to each other faster and the setting time will be less. And the third factor, which is based on the theory of setting, is the rate of growth of crystals. If the rate of growth of crystal increases, more faster they will come closer to each other and the setting reaction will get accelerated and the setting time decreases. So these are the three factors which comes under the theoretical factors. Now coming to the factors under control of manufacturer. Now number one is under or over calcination. Now calcination is a heating process and we know the temperature required is 110 to 130 degrees centigrade. Now if the temperature is less than 110 degrees centigrade, then some of the dihydrate particles will remain as dihydrate without converting to hemihydrate. And as everyone knows, as these dihydrate crystals, if they're present in the fresh hemihydrate stock, then they will act as the nuclei of crystallization and it will provide more number of nuclei, and so the rate of reaction increases and the setting time decreases. Now, when we say overcalcination, that means the temperature is going beyond 130. Now, as we have seen the heating cycle, if the temperature goes beyond 130 but below 200 degrees centigrade, then we get the particles of hexagonal anhydrite, which is the soluble type of anhydrite. Now, if you get the particles of hexagonal anhydrite, then it increases the rate of reaction because it is a soluble type. So it increases the rate of reaction and decreases the setting time. If the temperature goes beyond 200 but below 1000 degrees centigrade, then we get the crystals of orthorhombic anhydrite, which is the insoluble type of anhydrite. So in that cases, the setting reaction will be retarded and the setting time increases. So that is the effect of under and over calcination. It depends upon which type of crystals are forming, and accordingly either it will accelerate or retard the setting reaction. Now coming to the particle size. Finer the particle size, faster will be the rate of reaction and lesser will be the setting time. Then addition of accelerators and retarders. Now accelerators are nothing but the chemicals which when added to the material, these are the materials which chemicals which when added to the material, it will increase the rate of reaction and decrease the setting time. And retarders are the chemicals which when added decreases the rate of reaction and increases the setting time. Now, usually the accelerators, the mode of action of accelerator in case of plaster or stone is by increasing the solubility of the hemihydrate. and not the dihydrate. And the mode of action of retarder is it forms an adsorbed layer over the growing crystals, and thus it retards the rate of reaction. So there are certain chemicals which are used as accelerators. So most commonly used accelerators are potassium sulfate, sodium chloride. Of course, they have to be used in proper concentrations. Like sodium chloride in low concentrations, it acts as accelerators. But if you increase the concentration, it will act as retarder. Same with potassium sulfate also. Coming to retarders, borax is the most commonly used retarder in dental plaster or dental stone. Now, coming to the factors under control of operator. The first and the foremost is the cleanliness of the instruments. One of the requirements for mixing of any material that the instrument should be clean. Now, in case of plaster, there is a chance that some of the particles from the previous mix might get affected. Some of the particles from the previous mix might get entrapped into the fresh mix, and these particles are of the particles from the previous mix. So they are the particles of calcium sulfate dihydrate, which will increase the number of nuclei of crystallization. It increases the rate of reaction and decreases the setting time. So these particles of the set gypsum of the previous mix are also called as terra alba. Now, the second factor under control of operator is water powder ratio. Now, everyone knows that if you increase the amount of water within the practical limits, then the setting time increases. So, if the water powder ratio is more, rate of reaction will be slower and the setting time increases, and vice versa. Coming to the temperature of the water which is used while mixing the plaster. Now, temperature of the water from 0 to 50 degrees centigrade, there is hardly any change in the setting. But above 50 degrees centigrade, there is a gradual increase in the retardation occurs, and there will be increase in the setting time. Then at 100 degrees centigrade, as the solubility of hemihydrate and dihydrate is same, there will be no reaction. And above 100 degrees centigrade, a reverse reaction is seen. Then way of mixing. If you mix it rapidly within the practical limits, it is not prolonged, but if you mix it rapidly within the practical limits, then you're breaking one crystals into multiple crystals. That means you're increasing the number of nuclei of crystallization, and thus it increases the rate of reaction and decreases the setting time. Now, setting time. Now, in case of plaster or stone or any gypsum product, we find two setting time, that is initial setting time and final setting time. Initial setting time is that time from the start of mix till the material becomes hard or rigid. But it is not that hard. It can be carvable with the sharp instruments, but it is not moldable. And final setting time is that time from the start of mix till the material hardens completely. Now the material cannot be carved with your sharp hand instruments, but it has to be trimmed with the help of model trimmer. So that is the difference between initial and final setting time. Initial setting time, the material becomes hard, but it has not gained all its optimum properties which are meant for it. Now there are different methods to see the setting time. Now, these are the methods which has been mentioned, that is loss of gloss method, exothermic or rise in temperature, and penetration method. Now, loss of gloss method, that is when we mix the material, it has got a shine. But as the material starts setting, this shine is lost. Now, as this shine starts losing, that is one of the key point which tells you that the material is setting. It will not give you the exact setting time, but at least we get the idea whether the material is setting or not. Second is the rise in temperature. As everyone of us knows that this setting reaction is exothermic in nature, so heat will be evolved. So if you find warmness or rise in temperature, that shows again the material is setting. This also will not give you the exact setting time, but at least it gives the idea. Then third one is a penetration methods, which gives you the exact setting time. Now, penetration methods, there are two types of needles which can be used to measure the setting time. That is Vicat needle and Gilmore needle. Now, YCAT needle is mainly used to measure the initial setting time, and Gilmore, we have two needles, that is initial Gilmore and final Gilmore. Initial gives you the initial setting time and final gives you the final setting time. Now, both the needles have got different diameters, the dimensions are different, but the principle is same. So I will just tell you the principle of measuring the setting time. Now, the needles are suspended to this plunger, and here you have to place the test specimen. Now the needle, you have to press it inside the test specimen. From the start of mix till the needle no longer penetrates the specimen is your initial setting time, and the time from the start of mix till the needle no longer penetrates the surface only. It will barely causes a scratch. That is your final setting time. So this is the way you can measure the initial and final setting time. Thank you so much for your patient hearing, and the rest of the contents will be covered in my next lecture. Thank you.